Okay, this is Charles here. Can people hear me? Great. Okay, so it looks like Lavanya's had a little bit of technical troubles. So I'm just going to go ahead and jump into my talk. So if you have other questions for Jari, make sure to put those in the Slack community. So what I'm going to talk about today is something less practical and more connected to the mathematics of machine learning, which is why you should be thinking with negative log probabilities instead of probabilities. So machine learning is at the intersection of three separate areas of math, at the very least, but the most fundamental ones are definitely these three: linear algebra, calculus, and probability. And so these are old and like storied versions or types of mathematics. And so there's ideas about how these areas of math should be explained, what they're for. So for linear algebra, it's that it's algebra for solving equations with matrices instead of just numbers. With calculus, it's that it's for studying rates of change and for studying areas under curves. And for probability, it's that it's tools for manipulating distributions. But in the last couple weeks, I've been talking about how these traditional views aren't well suited to the problems that we have in machine learning, that linear algebra is not like algebra, and that there's a better way to sort of think about calculus. So in the two previous salons, I talked about how linear algebra is maybe a little bit more like computer programming, that it's the study of functions that can be represented by arrays more than it is the arrays themselves. There's also in the most recent salon, I talked about how calculus is more about using those linear maps to approximate functions, at least the way we use it in machine learning, where we mostly care about gradients. So I'm going to round out this series, at least for now, by talking about a better way to understand probability. And that's to think of probability as the mathematics of surprise. If you want something that's a little less poetic and a little bit easier to connect to other stuff, this is basically saying I'm going to go from the information theory perspective on probability rather than the measure theoretic probability or the statistical sort of approach to probability. And we're going to get there by thinking about what I call the surprise game, where modeling is a competition to see who can be the least surprised by the data. I'm going to contrast this competition with the way we solve debates in classical logic. If I claim X and you claim Y, the way we resolve our disagreement is that one of us provides a proof. So if I say 2 + 2 is 4 and you say 2 + 2 is 5, one of us needs to provide a proof that what we're saying is true or the other person's saying is not true. Famously, the debate between Socrates is mortal and Socrates is not mortal was one of the first debates done in classical logic. Turns out Socrates is in fact mortal. But logic like this doesn't immediately apply to most things in machine learning. Like this collection of pixels is a photo of a dog. There's no way to take our ands, our ors, our XORs, our disjunctive syllogi and all these tools and just answer that question. And if it seems to you a little bit surprising, I would consider maybe some examples of pictures like this from Twitter user @TeenyBiscuit. These are images. Some of them are chihuahuas, others are blueberry muffins, and it's actually pretty hard to tell which one is which. And some machine learning libraries, like publicly provided ones, struggle on this data set. And it's even harder to imagine how we might write down some set of some sort of set of basic logic that would tell us this picture has a dog in it or not. There's a whole bunch of other examples, things that happen in the future, like team A will beat team B, this stock's price will go up or this stock's price will go down, the number of deaths from coronavirus will be over 1 million. There are a lot of questions that we want to ask, but we can't use logic to answer them. So let's consider, instead of a debate involving proofs, let's consider a competition. Each of us writes down how surprised we would be for each possible outcome before it happens. This is how surprised I'd be if team A wins. This is how surprised I would be if team B wins. And it's important to say that it's no fair saying nothing surprises me. So there's a technical mathematical way to enforce that. But basically, you have to say that some things are surprising to you. Maybe everything's the same amount of surprising, but you can't just say everything is completely unsurprising. And then whoever is least surprised by the outcome wins the debate, at least this time around. And maybe you do this over and over and over again on many examples of Team A and Team B playing each other. Hopefully you wouldn't do it on multiple examples of the world suffering from the coronavirus pandemic. But in lots of other cases, you can do this over and over again. And from this setup of this game, of this competition of who could be least surprised, you can actually derive maximum likelihood estimation and the Kullback-Leibler divergence and a bunch of other tools that are actually where many of the loss functions that we use in deep learning and machine learning in general come from. Things like the cross entropy or even the squared error or the absolute error. We can get them using this framework by just thinking of them in terms of this idea of surprise. And so when I have something pretty specific in mind when I talk about surprise. It's just like people have a specific thing in mind when they say probability, even though we have this informal notion of chance. So if something is just a little bit less probable, it happening is just a little bit more surprising. And if it's a lot less probable, it's a lot more surprising. If something is certain, it happening is not at all surprising. And if something is impossible, it happening is more surprising than anything else. So numerically, this is saying that our surprise is a continuous function of the probability. That's the first thing. Tiny changes in probability mean tiny changes in surprise. And if something is certain, it being not surprising, means that if something has a probability 1 of happening, the surprise is 0. And then if something is impossible, if its probability 0, then its surprise is infinite. That's the only way that it can be more surprising than anything else. The important difference between probabilities and surprises is that where probabilities multiply, surprises add. So if two unrelated surprising things happen, we just add those two surprises together. So this is the equivalent of the probability rule, which is that if two things are independent, then we multiply their probabilities to get their joint probability. And so it's the same basic rule, but now we're going to use a different mathematical operation to do it, addition instead of multiplication. And together, these define a mathematical notion of surprise. So this is a function of the outcomes, just like the probability is a function of the outcomes. And we can define it in terms of the probability, that it's the log of 1 over the probability. This is also known as the surprisal. And I think I titled this talk originally surprisal. It's not a super well-known idea on its own, not something that people often feel like they need to give a name. So it's a little bit open-ended, and I think surprise rather than surprisal is the right name for it. It's kind of a silly-sounding name, surprisal. So this surprise is the thing that when we do information theory, we take expected values or averages of this to get the quantities that we're interested in, things like mutual information and entropy and stuff like that. So if you want to go further with this set of ideas, then go ahead and check out stuff about information theory, and they're going to run with this idea. But very few approaches to information theory actually start by defining this thing, the surprise, and then going on and defining everything else. They usually start with something like the entropy. So one exception is this guy, Edwin James, who is one of the original Bayesians and maybe contributed more to Bayesian inference than Bayes did himself. So he has this great text, Probability Theory, the Logic of Science, that starts by defining the surprise and the probability and goes from there. So I'd strongly recommend that as a way to learn information theory that's very relevant to what we do in machine learning. But we're going to focus on things that are just about this surprise function and not about information theory quantities. So we're not going to take these expectations and things that they do in information theory. So the first is a very simple one, which is some folks in statistics have started to say that you should use the surprise instead of the p-value to communicate your results. So this is something that's maybe going to make more sense to folks who've done some traditional statistics, folks with like a medicine background or a science background where these quantities get used. So using surprise might actually make it easier to interpret and understand the outcomes of your hypothesis tests. So the p-value is what people usually use. They say they do all of their statistics, they do all their experiments, they want in the end to know, is this something that could have happened by chance because of something uninteresting, the null hypothesis. And what people want the p-value to mean is something like the chance that the null hypothesis is true. I am trying to demonstrate that the moon is made of cheese. The null hypothesis is that it is not. And so I would like to be able to tell people the moon is definitely not made of cheese. So this p-value is small when it's unlikely that the null hypothesis is true. That's what people would like it to mean. But in fact, it's actually the other way around. So it's, instead of it being the probability of the null hypothesis when we've gotten a positive result from our statistical test, it's the probability of a positive result on our statistical test if we assume the null hypothesis. And it's basically backwards from what people actually want. But unfortunately, the thing people actually want is much harder to get. And so people calculate this thing, the p-value, then they misinterpret it as the thing that they really actually wanted. So one suggestion that's, I'm going to link to this archive paper that puts it out there. It's also something that the American Statistician, the Journal of the American Statistical Society, one of the major ones, they've also put this idea out there. Instead, we should do the logarithm of 1 over the p-value. And what that says is I'm trying to communicate to you how surprising my results are to somebody who is a skeptic. How surprising are my results if you believe this null model, this model in the null hypothesis. And they go in opposite directions, right? A large S is the kind of thing that you would get if you have a publishable result, whereas a low P is the thing that you have that you want in order to have a publishable result. But apart from that superficial difference, there's a lot of more substantial differences. And so this paper goes into detail about them, but it discourages this misinterpretation of the p-value as a probability and helps you, has a lot of additional benefits as well for combining information across studies and for being able to better disambiguate between really strong evidence and moderately strong evidence and things like that. The other thing that surprise is useful for is it is useful for thinking about the densities and distributions that we work with when we do probability, when we use probability in our machine learning. And so I'm going to borrow this example that I saw on Twitter and ask, just looking at these, which of these do you think is a Gaussian? So which of these is a normal distribution or a bell curve? To me, they all look like bell curves in some loose sense. And it's really hard for me to tell. I would have probably said that all of these, yeah, those all look kind of like a Gaussian to me. But in fact, only one of these is actually a Gaussian, and it's the one in the top left. The others, the logistic distribution is pretty close to the Gaussian in a lot of ways, but the others, the Cauchy distribution, is one that actually has infinite variance. So there's no standard deviation to this distribution. It's so wide. The beta distribution is the exact opposite. The beta distribution down in the bottom right corner is actually 0 outside of the range from -4 to 4 that this is that's in the center of the plot. And that's a huge difference. Under this distribution, nothing outside of ±4 can be generated. That's a very big difference. But if we just look at these probability densities on their own, it's really hard to tell the difference. And this seems like really bad. It would be great if the way that we mathematically represented our distributions made these kinds of differences like plain as day. The way they would be if you actually started, sampling from these distributions. So logarithms of densities are easier to compare. So this surprise is going to make our densities easier to compare to each other. The important differences in our probability distributions are often in the really unlikely events, in the tails. Is this a once in a year event or a once in a millennium event? The raw values are really close, right? 1/3 365 is only about 1 over 365 away from 1 over 365,000, thinking of these as numbers. But their logarithms are actually, relatively far apart. There's basically 3 orders of magnitude between them. So if I log 10, the difference of those 2 logs is going to be 3. So that makes these things that are actually very, very different, that would be experienced very, very differently if you were to draw samples, actually look different once we write out the numbers. And in addition, logarithms of densities are actually even easier to work with. So a lot of densities have a very simple form in the log. Like the Gaussian, on the left, we have the usual way that people write the Gaussian distribution in terms of its probabilities. And so we've got an exponent, we've got like E on the bottom, and then stuff in the top. And I look at that and I don't immediately know what that function looks like or what's going to happen if I add 2 of them together or multiply 2 of them. It's kind of confusing. But if I take the logarithm, then that E disappears. And what I have instead is just a parabola. I have x minus mu squared. And for me, parabolas were something that I encountered really early in my mathematics education, grade school. And so that's something that I've gotten a chance to use a lot and I'm comfortable and familiar with. So these types of densities that have these really neat, clean forms when they take the logarithm, or that are easy to mathematically work with once you take a logarithm, are called exponential families or log linear families. And they're all over the place in sort of more older school structured statistical approaches. And then they sort of bleed into deep learning and machine learning. If you look at variational autoencoders, there's going to be lots of pieces of them that use these exponential or log linear families in them. And so these are just, they happen to be the class of densities that we can do math easily with. And that allows us to do machine learning, create algorithms with these densities. And they'll be easier to understand, easier to think about in a lot of cases if you look at them with their logarithms. So on this slide, I told you that the Gaussian distribution becomes, with the logarithm, it becomes a parabola. So looking at these are the same 4 distributions. I changed the order. So it's not, or maybe I didn't. So it's not definitely the one in the top left. But these are the same 4 distributions, but now I'm showing you the logs instead of the raw densities. So this would basically just take that previous plot, put it in a log scale in Python, single line. And what's interesting about this to me is that they look super, super different from each other now. So we can see that one of them is sort of zooming off to infinity, the one in the top left. We can see that the one in the bottom left and the top right, that those 2 are not going down nearly as quickly as the one in the bottom right. So the one in the bottom right is going down really quickly, and the pace at which it is going down is getting faster and faster, right? So the slope is increasing as we go in, as we go out from the middle, and that is that's a characteristic of a parabola. This guy in the bottom right-hand corner is pretty easy. Once you know what to look for, it's pretty easy to identify this guy as a parabola, and that's our Gaussian, and the others are the different ones. And it makes it clearer that what's different between this logistic and this Cauchy, both of which looked pretty similar to the Gaussian before, is that the way they go to 0 as they go away from the center. So there's actually a lot more that you can learn just from comparing these 2 ways of looking at distributions. And I recommend you check out this example blog post by this guy, Ryan Moulton, that goes into more detail about how to use these things. And I'll pop a link to these slides into the chat once I get to the end. And then lastly, the great thing about these surprises is that they connect Bayes' rule and linear algebra. And these are 2 of my favorite things. So anything that comes in, in the middle of them is got to be great. So one pithy way to state this is that with surprises, we can treat our beliefs like vectors. So the reason why this happens is that logs turn multiplication into addition. So on the left here, we've got the negative logarithm takes things that are positive numbers and turns them into just any old number, some of them negative, some of them positive. And e to the minus x takes a number x that's positive or negative and makes it solely positive. So and these two things are opposites of each other. So this is called an isomorphism. So it says that these two things, we've mapped one onto the others, And in particular, what this does is it takes things that were addition for our positive and negative numbers, for what basically you can think of as floats or real numbers. It takes addition in the real numbers and it turns that into multiplication in the positive only numbers. So that's in the top right corner of this slide. A plus b is turned into e to the minus a times e to the minus b. So where before we would have added two numbers, now if we multiply those two numbers together. And if we use this, we can define a vector space of probability distributions in a straightforward way. So what we do is we take this e to the minus operation and we apply it to all vectors of length n. And that gets us all positive only vectors of length n. So we basically take that n-dimensional space over there on the left and we map it all together into the upper right-hand quadrant, the positive only quadrant. And then we can take that, and if we divide those by their sum, then we end up with only things that add up to 1, only vectors of length n that add up to 1. And those describe probability distributions on n outcomes. So in this case, n is 3. So this is all probability distributions with 3 possible outcomes, 3 possibilities. So like, I guess there aren't 3-sided dice, there aren't 3-sided coins, but something that could take 3 possible outcomes. And now, if I want to know, and I also have that negative log that takes me backwards from the positive only vectors of length n to all vectors of length n. So that'd be an arrow pointing to the left underneath e to the minus. So if I want to add together two probability distributions, if I want to define a notion of addition for probability distributions, I take their negative logarithm and add that together. And so I take the negative logarithm to turn them back into just a generic vector of length n, and then I add them together. That allows me to define a notion of vector addition for probability distributions. And I can do the same thing for scalar multiplication. The other nice thing about this way of thinking about probability distributions is that it's actually something you've seen before. If I combine these two operations, what I'm doing is I'm taking something, e to the minus something, that I'm dividing by the sum of those things, and that combination is what people call the softmax function. So e to the something divided by sum of e to the something, that's softmax. So what softmax is doing is it's taking things that are like normal vectors and turning them into probability distributions. And the new thing that I'm adding in this discussion here is I'm saying, let's not just think, oh, I've sort of taken these numbers and just sort of normalize them so they sum to 1. That's not that interesting. Is that now we know how to we can take things that we could do to vectors of length n, right? We can add them together and subtract them and multiply them by numbers and apply matrices to them and calculate eigenvalues of those matrices and all these things. We now do that with probability distributions. We just map them backwards with minus log, with minus log, and then we apply our operations, and then we come back if we want the probability distributions at the end. And the addition in this vector space is Bayesian updating. What used to be with probability distributions, it would be multiplying two things together. But when we use minus log to turn them into vectors that we can add, then we're now adding them together. So on the left-hand side, we have the likelihood and the prior thought of as surprises. And on the right-hand side, we have the likelihood and the prior thought of as probabilities. And so minus log turns our probabilities into surprises and allows us to add them instead of multiplying them together. And all the normalization stuff gets included as part of that transformation once we turn things back into probability distributions. So this is part of how I think about lots of deep learning models that have a softmax in them, like some kinds of attention models and some kinds of categorization, like categorical models, classification models, that what they're doing is inside the network, they're working to build up a nice representation of this vector space that's on the left-hand side here, where all the stuff that I want to do with like complicated inference is, just simple addition. And then at the very end, I use something like softmax to turn it into a probability distribution to use it for something else. So this example comes from Tom Leinster at the N Category Cafe. He goes into more detail about it and focuses on an example from statistical mechanics from physics. So the takeaways are that these surprises are negative log probabilities, and they give us another lens for understanding uncertainty. And it complements normal probabilities. Some things that are really easy to understand with surprises are a lot harder to understand or to see with probabilities. And then vice versa. Some things like taking an average are actually kind of hard with surprises, but really straightforward with probabilities. So it's not necessarily that one is better or worse than the other. It's just that they are both useful perspectives. So when I need to do a problem in probability, when I need to understand what's going on with some new deep learning model that has some probabilistic components to it, I try and attack it with both. But if the thing that gives me a sense that maybe the log probability way of thinking about it is going to be more important is any time that there's multiplication of probabilities, which is really often. It's in Bayes' rule, it's in independence assumptions, it's in conditional probabilities, all kinds of places. Anytime there's multiplication, a logarithm is going to turn that into addition, and it's usually easier to think about adding things rather than multiplying them. So I wanted to put this out there just because you might see people talking about log probabilities when they're doing a derivation, or if you look in TensorFlow probability or PyTorch, Pyro, or any other probabilistic programming library, you're going to see log probabilities everywhere. And most people will say, oh, it's for convenience to simplify our derivation, to make things mathematically, make things numerically easier on a computer, to make sure that there's not overflow and underflow. And people act like it's like something to be embarrassed of or unimportant, but it's actually, there's a reason why it makes things easier. There's a reason why it makes things cleaner. And I think it's important to have that in mind so that in the future you can make other things easier and other things cleaner with log probabilities. So hopefully that was useful. I'll include some links to additional blog posts and material that goes into greater depth on these things. With that, I'll take any questions that anybody's got.
There are some questions in the Ask a Question tab, Charles, if you want to hop on there.
Yeah.
And I don't see anything in the Slack so far.
Okay. Okay, so so question from Mani. Why not 1 over p? Why log 1 over p? Does log help magnify the value to be able to see it closer? So yeah, actually, so lots of the things that I said, 1 over p would have worked pretty well. And there actually are lots of, logs and regular probabilities aren't actually, the only two ways people think about these same ideas. And I remember correctly, there are some ways that use inverse probabilities also. But the real bonus is that is what I kind of probably got to a little bit out of after you asked this question. It's that this logarithm is what gives you the turning multiplication into addition, and that also means that it turns the things that were ratios into differences. And so things that used to be ratio spaced from each other become linearly spaced. So this is something we've all had to learn during the coronavirus pandemic. The people tend to show the cases with by taking the logarithm of the number of cases. So they show log scaled plots. And that's because with something that grows exponentially, it's less useful to think about the absolute differences between things and more useful to think about their ratios. And so another way of saying a lot of things I said in this talk, is that probabilities are the kind of thing where you care about the ratio, not just the absolute differences. And yeah, so for the other things, I will include once this guy is posted, I will include some links to additional stuff about softmaxes and about uncertainty and inference. I will say that, yeah, I have I taught a course on Bayesian inference at Berkeley in the fall that sort of presents things, some from this perspective, but actually maybe a better one would be Statistical Rethinking by Richard McElreath. So that one is primarily in R, but people have translated it into TensorFlow probability at least, and I think also Pyro. And that one, if you Google that, you should be able to find it. There's videos online there, and in addition, it's a textbook and exercises. So that would be where I would go to get some of this education. Yeah.
Cool. Thank you, Charles. Does anyone have any more questions for Charles before we? Do you have something more for us to next time, Charles? Or is this it?
Well, that's the end of this series, so I have to come up with something else to talk about. I might talk about my thesis, but I'm, kind of tired of talking about that.
Maybe we'll give you a break and maybe have you on like a couple of months from now. Thank you, Charles.